Hello, welcome to Understanding Power Electronics. In this video, we will see the boundary operation between continuous conduction mode and discontinuous conduction mode of a buck DC-DC step-down converter. With that as our aim, let's get started. This is the buck step-down DC-DC converter. We will briefly go through some background material dealing with the operation of the buck converter in continuous conduction mode. In case you are not familiar with the continuous conduction mode operation of buck converter, there are two earlier videos in this series on CCM, or a continuous conduction mode operation of buck converter. It will be good if you can go through that. Then you will be able to follow this video more easily. We will now briefly go through the operation of a buck converter under continuous conduction mode. We will go through just what is needed for understanding this video. This is the VA waveform, that is the voltage waveform at node A. T on, T off and Ts, or the switching interval. The duty cycle is T on by Ts. When the switch is on, node A is connected to V in and the voltage will be V in. When the switch is off, the inductor current will freewheel through the diode and VA will be 0. We are treating the components, the switch and the diode, as ideal. The average of VA voltage is the output voltage. The LC filter filters the ripple and passes the DC through. When the switch is on, the positive side of the inductor is connected to V in, the negative side is connected to V naught. So the inductor voltage is V in minus V naught. When the switch is off, the diode conducts and the voltage minus V naught is applied across the inductor. So the inductor voltage toggles between V in minus V naught and minus V naught. The rate of change of current in the inductor will depend on the voltage across the inductor. So we can plot the inductor current as shown. The slope during the on interval is V in minus V naught by L. Inductor slope during the off interval is minus V naught by L. So the inductor current goes from I1 to I2 with a slope of V in minus V naught by L and returns to I1 with a slope of minus V naught by L. Delta IL is the peak-to-peak ripple current, that is I2 minus I1. We can find the delta IL by taking the slope of the current multiplied by the interval T on. With a bit of manipulation, we can show delta IL is V in Ts by L times D times 1 minus D. If you express it in terms of V naught instead of V in, that will be equal to V naught Ts by L times 1 minus D. That is the peak-to-peak ripple current in the inductor. The average of the inductor current is the output current I naught. I naught is determined by the output voltage and the load connected. Notice that the average of the VA voltage is the output voltage equals dV in, duty cycle times the DC input voltage. In this expression, there is no place for load current. So the output voltage V naught does not depend on the load current. Ideally, it does not depend on the load current. Practically, it will depend on it a little bit. Now, if you look at the ripple current, the slope of the inductor current during on interval is V in minus V naught by L. V in is a fixed value, L is a fixed value. V naught does not depend on the load current. For a given duty cycle, that is a fixed value. So V in minus V naught by L is a fixed slope. It does not depend on the load current. Likewise, the slope during the off interval minus V naught by L, that is also fixed, does not change with the load current. So the ripple current does not change with the load current under continuous conduction mode. Number one, the load voltage does not vary with load current under CCM. Number two, the ripple current waveform, delta IL value, they do not change with load current under CCM. Keep that in mind, we will use it soon. Now, when the switch is on, the inductor current flows through the switch. When the switch is off, the current freewheels through the diode, so the inductor current flows through the diode. So this part of the inductor current is the switch current. This part of the inductor current is the diode current. I will just plot the switch current here just to show how it can be done. So this is the switch current. We are just taking that part of the inductor current and drawing it separately. In the previous videos, we saw the detailed waveform and understood how buck converter operates under CCM. Next, we will see how boundary current operation occurs. This is again the inductor voltage waveform, toggling between Vin minus V0 when the switch is on and minus V0 when the switch is off. And this is the inductor current waveform. When the voltage Vin minus V0 is applied across it during on interval, the slope of the inductor current is Vin minus V0 by L. When the voltage minus V0 is applied across the inductor, the slope of the inductor current is minus V0 by L during the off interval. In the complete interval T off, the inductor current is flowing and it is flowing through the diode. The average inductor current is the output current. Here it is marked as I01. I01 is the output current at this point of operation of the converter. Now let's vary the load and let us reduce the load current. If you are using a resistive load, reducing the load current means increasing the load resistance. You can say that I02 is less than I01. V0 remains the same. If you are under continuous conduction mode operation, delta IL remains the same. The ripple current waveform remains the same, but the DC current has come down. Now let's reduce the load current even further. So I03 is less than I02, less than I01. Again, the output voltage remains the same and the ripple current waveform remains the same as before. We can continue this process. We can do one more step, one more reduction in the load current. We have reduced it to I04 now. Now you can see that this valley point of current is getting closer and closer to the axis. It is getting closer and closer to zero value. So at I04 also, the load current is low. I04 is less than I03, etc. But the ripple current waveform remains the same. The output voltage remains the same. Let's reduce the load current even further. Now, the inductor current at the end of the cycle just comes and touches zero, and immediately the switch is switched on and the inductor current starts to rise again. DC current corresponding to this is I05. It is the average of this orange waveform. You can view that the operation is still under continuous conduction mode. V0 is the same, is equals dV in, and the peak-to-peak ripple current is as before. The ripple current waveform hasn't changed. It is just that it is hitting zero here at the valley point. Suppose we reduce the load current still further. Let us assume that V0 hasn't changed, that the ripple current waveform remains the same, peak-to-peak ripple current remains the same. So we are making the assumption that somehow it is still in continuous conduction mode. Then what will happen? That whole current, ripple current, will go down further. That is the waveform shown here. Now you see what is happening. During the T-off interval, the diode current comes down and hits zero here. And then it is expected to go negative. Because we are applying across the inductor a negative voltage, it brings the current to zero and then forces it to go negative. Switch is off. That means we are expecting the diode to take a negative current, which can't happen. So such an operation cannot occur. We cannot reduce the load current below I05 and expect the operation to be in CCM still. I05 is the minimum load current at which CCM operation is possible. So I05 is the boundary, is the lower limit of continuous conduction mode. So let's remove this current. I04, I03, I02, I01, all these currents are higher than I05 and all of them are in continuous conduction mode operation. So when the output current is more than I0B, it is continuous conduction mode operation. When the output current is less than I0B, it is discontinuous conduction mode operation. That we have not seen that yet. That is another mode of operation of the converter. When I0 exactly equals IOB, we are operating at the boundary. So here the converter has 1 foot in the CCM land and 1 foot in the DCM land. So CCM equations V0 equal to dV in, that will be valid. Equation for delta IL, that will be valid. DCM equation, which we will derive in the subsequent videos, those will be valid also. Now let us see intuitively what factors may influence the boundary current. I have taken one of the load currents, I04, made the line thicker. We will focus on that waveform. Now focus on the downward slope. Downward slope is minus V0 by L. If V0 by L, the slope is higher, even from a higher current, you can come down and hit zero. So I0B will be proportional to V0 by L. Another factor that will influence is the T-off interval. If the T-off interval, again focus on the I04 waveform, if T-off interval happen to be larger, then the downward slope is more likely to come and hit zero. So even from a higher current, you can come down and hit zero if T-off interval is larger. T-off interval is 1 minus d Ts. So IOB intuitively is proportional to T-off, which is 1 minus dTs. IOB is influenced by the downward slope of the inductor current during the off interval, that is V0 by L. IOB is influenced by the off interval itself, which is 1 minus dTs. IOB is proportional to V0 Ts by L, 1 minus d. So now we will derive an equation for the boundary output current. Again, the inductor voltage waveform. This orange curve is the boundary inductor current. It starts from 0 at the start of T on, goes up at a slope of V in minus V0 by L, goes to some peak value IP, and then when we switch off, the inductor current freewheels through the diode for the whole of the T off interval and comes down to 0 exactly at the end of T off interval. Immediately, the switch is switched on again and the cycle repeats. And we know that the average of the inductor current is the output current. So this is the inductor current under boundary condition IO5, which we saw earlier, and the average of that is the boundary current. This is the peak-to-peak ripple current delta IL, which is of course equal to IP itself, the peak current itself. So we want to determine the value of IOB. Some of you might notice immediately that IOB is nothing other than delta IL by 2. But let's go through the formal steps. The average current, IO5, which is the boundary current, is 1 over Ts integral 0 to Ts IL dt. Integral 0 to Ts IL dt is simply the area of this triangle AB. That will be half IP times Ts. You have to divide by Ts to get the boundary current. Ts and Ts will cancel, so Ip by 2 is the boundary current. Ip is the same as delta IL, and delta IL we saw it is V in Ts by L d times 1 minus d. We can write this equation in terms of V naught also, which is V naught Ts by L 1 minus d. V in d is V naught. So this divided by 2 is your boundary current. IOB is V in Ts by 2L d times 1 minus d, or which is the same thing as V naught Ts by 2L 1 minus d. So ripple current divided by 2 must be less than I naught for CCM operation. Let's compare it with our guess earlier. Earlier we guessed that I naught B will be proportional to V naught Ts by L times 1 minus d. Now it is V naught Ts by 2L times 1 minus d. So not bad. So intuitively what we thought and the equation matches. Next we will normalize the boundary equation. Normalization is a thing that many times engineers and scientists do in their disciplines. Why do we do normalization? Normalization of equations, design equations and other equations, we do in order to compare across scales of design. Suppose I have designed a buck converter, a 100 watts converter operating at 100 kilohertz. Another person has designed a buck converter operating at 10 kilohertz and delivering 5 kilowatts of power. How do we compare the two? Is my inductance relatively large compared to the other person's design? How do we say that? For that, we should have a common basis for comparison across scales of design. So that's a reason why we do the normalization. It allows one to see where in the design space we are. It also simplifies the equations and lumps the parameters together so that the understanding and the plotting of curves becomes simpler. Let's take the boundary equation that we developed just now. IOB is V in Ts by 2L d times 1 minus d. I want to plot the boundary current versus duty cycle. That means I'm interested in how IOB varies with duty cycle. Notice that I have V in as a parameter there, the input voltage. Ts, the switching period, is a parameter there. L, the inductance, is a parameter there. So if I just plot IOB versus D, I have to plot one set of curves for V in variations, another for Ts variations, maybe a third set of curves for inductance variations. It becomes too complex. And we can see very simply by taking this V in Ts by 2L from the right hand side to the left hand side, dividing IOB by V in Ts by 2L, we can get a dimensionless equation relating IOB by V in Ts by 2L and D. That's what normalization does. We can take V in Ts by 2L as the base current. The unit of V in Ts by 2L, as you can see, is current because D is dimensionless. 1 minus D is dimensionless. So the left hand side it is amperes. The right hand side must be amperes. So V in Ts by 2L must be amperes. You can check it out. In general, if Vn and In are chosen as bases, then any voltage Vx will become a dimensionless quantity Vxn by dividing by Vn. Likewise, any current Ix will become a dimensionless quantity by dividing by the base In. If Vn and In are the voltage and current bases, then the resistance base or the impedance base will be Vn by In. Vn times In will be the power base, and so on. Remember that multiple sets of bases are possible. Usually, one set of bases will stand out for our use. Let's take the boundary current. V in Ts by 2L d1 minus d. If you express in terms of V in, if you express in terms of V naught, it will be V naught Ts by 2L times 1 minus d. So for the voltage base, obvious choice will be either V in or V naught. We can call it as base V in, base V naught. In this video, we will use base V in. We will use the voltage V in as the base. It is kind of an obvious choice. You know the voltage, so I'll use that as a base. Using the output voltage as a base has certain advantages in some applications, in many applications. We'll see that later in another video. So with this base, the base voltage Vn is V in. The base current, it is very convenient to take V in Ts by 2L. The boundary current IOB divided by In, the current base, will give us the normalized boundary current. IOB by In is simply d times 1 minus d. So IOBN is a dimensionless quantity. Dn minus d are dimensionless quantities. So this equation has no dimension. Remember, at boundary operation, V naught equals to dV in is still valid. So I can substitute for d V naught by V in. So this will be V naught by V in times 1 minus V naught by V in. And V naught by V in is VON, because V in is the voltage base that we have chosen. So IOBN will be equal to d times 1 minus d equals VON times 1 minus VON. Our boundary equation has now become a dimensionless equation. We can now plot this equation. So we are plotting the buck converter CCM DCM boundary. The y-axis is VON. The x-axis is ION. So you can recognize that this is a parabola but shifted by 90 degrees. Now this point is the maximum boundary current that occurs at 0.5, VON equal to 0.5. You can differentiate this with respect to VON, set it equal to 0. You will get the VON equal to 0.5. And if I now put VON equal to 0.5 here, IOBN, that maximum value, will be 0.5 times 1 minus 0.5, 0.5 times 0.5, which is 0.25. So at VON equal to 0.5, maximum normalized boundary current occurs, that is 0.25. So this is the boundary current. In this region, ION is more than the boundary current, so the operation is in CCM. Within this parabolic region, ION is less than IOBN, so you are in discontinuous conduction mode. We haven't still studied discontinuous conduction mode, but we know definitely it's not in CCM. Next, we will see the CCM characteristics on this graph. In other words, we are integrating the boundary current and the CCM characteristics. We know the CCM characteristics already. V naught by V in equals T. V naught by V in, now under this normalization, it is VON. So VON, the normalized output voltage, is the duty cycle. So let us plot the CCM characteristics for D equal to 0.1. So at D equal to 0.1, VON is equal to 0.1. The value of VON does not change with the load current. It does not change with ION, normalized output current. So it's a horizontal line. But this is the CCM region. This is the boundary. So this line extends only up to this point. When the normalized current is less than this equation will not be valid. So this is the characteristics of the buck converter under CCM when d equal to 0.1. Now we can plot a similar line for d equal to 0.2. That is d equal to 0.2. Again, when d equal to 0.2, V on equal to 0.2. If the load current is less than this boundary current, you are entering into the DCM region. The CCM equation is not valid. So we stop right there. Plotting the CCM, we stop right there. Likewise, I can plot for d equal to 0.3, d equal to 0.4, d equal to 0.5, and so on. So we have combined the CCM operation characteristics of the converter together with the CCM DCM boundary. Notice where we are going. In the next couple of videos, we will be developing the DCM characteristics also and integrating that with this, so that we will get the complete characteristics of the buck converter under CCM, under DCM, and at the boundary operation. Next, we'll do a simple problem to illustrate the concept that we have learned. V in is 100 volts, D is given as 0.3, Fs switching frequency is 50 kilohertz, and the minimum current and the maximum current are given. The maximum current is 21 amperes and the minimum current is 7 amperes. But the capacitor is treated as being high, so that the output voltage is practically ripple free. We are asked to determine the minimum inductance such that the operation is always in continuous conduction mode. A fairly straightforward problem. Let's attempt that. Ts, the switching period, is 1 over Fs, 20 microseconds. I0 has to be more than or equal to I0b for CCM. And I0b is V in Ts by 2L d times 1 minus d. So I0 must be more than this. And you can rewrite this inequality as L must be greater than or equal to V in Ts by 2I0 d times 1 minus d. So you just have to put in the values. So which I0 will you use? Will you use 7 amperes or 21 amperes? In other words, L minimum, the minimum inductance has to be more than this. Will you use the largest number on the right hand side or the smallest number on the right hand side? Sometimes I find that students can get confused with it. To clarify that, let's use this example. This picture is courtesy of Copilot Bing. Now let us say an engineer has to design a door such that all the children in the school can go through it without bending. So the minimum height of the door should be more than the tallest child in the school. So the minimum inductance that we use must be more than the greatest value on the right hand side. The greatest value on the right hand side you get when I0 is at its minimum. That means I0 has to be minimum. We know that already. As we go lower in output current, you have more chances of going into DCM. Using I0 equal to 7 amperes and plugging in other values, we will have L must be greater than this quantity. If you evaluate that, that is 30 microhenry. In some places, this is called as critical inductance. L has to be more than this value. Notice that we have taken an ideal converter, and also in practice, there will be component variations. So for these reasons, it is normally a practice to take a slightly higher value. So instead of 30 microhenry, we might actually use 32 microhenry or 35 microhenry, so that we make sure that the operation is in continuous conduction mode at 7 amperes, that is the minimum current. Now we will use the normalized characteristics we developed earlier to view the operation of the converter under minimum load and maximum load. This is the buck converter characteristics under CCM operation plus boundary operation. We are using base V in, Vn is V in, In is V in Ts by 2L. So our normalizing factor or the base voltage is 100 volts. Our base current or normalizing factor for current is In equals V in Ts by 2L. V in is 100 volts, Ts is 20 microseconds, L is 30 microhenry. Let's assume that we have not given any margin. Then we can calculate it is 33.33 amperes. This is the base current. V in is 100 volts, duty cycle is 0.3. So the output voltage is 30 volts. And the normalized output voltage, VON, is VO by V in. That is 30 by 100, 0.3, which is of course the duty cycle. We already saw that VON will be equal to the duty cycle. So VON is equal to 0.3. So I'm just plotting it here. I just thickened the line. This line, of course, stops at the CCM DCM boundary as we saw earlier. The two currents are 7 amperes and 21 amperes. ION max, that is the normalized maximum current, is IO max 21 amperes divided by the base current 33.33 amperes, which is 0.63. The minimum normalized current is ION minimum is IO minimum by IN 7 amperes by 33.33, which will be 1/3 of this 0.21. So the normalized currents is varied between 0.21 to 0.63. Remember that these are dimensionless quantities. So it's not 0.21 amperes, 0.63 amperes. Now we can do a little cross check. This minimum ION must be on the boundary. So let us check it. IOBN, that is the boundary normalized current. Just a short while ago, we showed that it is equal to VON times 1 minus VON. That is 0.3. VON is 0.3. That is 0.3 times 1 minus 0.3. That is 0.21, which is the same as this. So the minimum normalized load current is the same as the normalized boundary current. So that is this point here, 0.21. So which is as we designed. So everything is all right. ION max 0.63 marked here. ION minimum 0.21 marked here. That is right on the boundary. Next, we will look at the voltage regulation. In this case, the voltage regulation becomes trivial, but still it's a good exercise to think in terms of voltage regulation when we are looking at this problem. Percentage voltage regulation is defined as V0 no load minus V0 full load divided by V0 full load times 100%. If you are talking of a transformer, this is how you will define it. Here we can define the voltage regulation as V0 minimum load minus V0 maximum load divided by the V0 maximum load times 100. So what it measures is how much does the output voltage change when the load goes from maximum load to minimum load. Here V0 minimum load is 30 volts. V0 maximum load is 30 volts. So this is obviously 0%. Ideally. If you are seeing here, you can see that the normalized value of the voltage has remained constant. So there is no variation in voltage as you reduce the load or increase the load. So percentage regulation is very good, 0%. That's what you want, right? In practice, however, this will not be the case. The power semiconductor switch will have some voltage drop. The diode will have some voltage drop. The inductor will have some losses. All this will add up and you will have some drop in the voltage as you increase the load. We will zoom into this graph and we have shown it here. the voltage drop. So the voltage curve will droop. This is the case with transformer also. As you load, you can expect the voltage to drop a little. So it will not be a perfectly horizontal curve, a little droop will be there. With this, we have come to the end of this video. In this video, we have looked into the boundary operation of a DC-DC buck converter, how and why this CCM DCM boundary operation occurs. We derived an equation for the boundary operation. We normalize the equation so that we can compare across scales of design. We also integrated the CCM characteristics and the boundary characteristics together and plotted the buck converter characteristics. Lastly, we saw an example problem to understand the concepts better. If you like this video and this series of videos, please subscribe to this channel and click the like button. Thank you very much.